All right, let's dive into a vulnerability that's, well, a true legend in web security. We're talking about injection. It's been around forever, but it's still haunting applications all over the world. It's landed at number 5 on the brand new OWASP Top 10 for 2025. So today, we're going to break down exactly what it is, see how it works in the wild, and really get into why this thing is so incredibly tough to stamp out for good. So you hear it's dropped from number 3 a few years ago to number 5 now, and you might think, hey, that's great news. We're making progress. I mean, that sounds good, right? Is this classic, stubborn problem finally on its way out the door?
Well, not so fast. Take a look at this. Despite the drop in rank, injection has more associated CVEs, that's common vulnerabilities and exposures, than any other category, by a lot. So what's going on here? It seems that modern frameworks are getting better at stopping the simple stuff, which brings the average severity down. But the sheer number of places an application can accept input today means the vulnerability itself is actually more widespread than ever.
And if you needed one number to really drive that point home, here it is: 100%. According to OWASP's data, injection flaws are found in pretty much every single application they put to the test. So yeah, the ranking may have shifted, but the reality for developers and security teams on the ground, it's still a massive problem. Okay, so what are we actually talking about when we say code injection? Let's get right to the heart of it. At its core, it's all about a fundamental breakdown of trust. Here's the key idea. An injection vulnerability happens when an application gets confused. It can't tell the difference between plain old data that it's supposed to handle and a command that it's supposed to execute. An attacker sends in some cleverly crafted input, the application just passes it along to something like a database or the operating system, and bam! That system runs it. The attacker's data just became executable code. And you have to understand, injection isn't just one thing. It's a whole family of related attacks. You've got the classic SQL injection, of course, but it also targets modern NoSQL databases, the server's operating system itself through command injection, directory services with LDAP injection, and even the frameworks we use with template injection. And yes, even cross-site scripting, or XSS, is considered part of this big, dangerous family. Now, inside this family, the risk can be totally different. On one hand, you have something like cross-site scripting. It is everywhere. Look at that CVE count, over 30,000. But often the impact of a single XSS bug is kind of limited. Then you have SQL injection on the other hand. It's less common, but a single successful attack, it can be absolutely catastrophic. We're talking a full data breach from just one flaw. Understanding this trade-off between frequency and impact is crucial. All right, enough theory. Let's see how this actually works. We're going to walk through a couple of classic attack scenarios that show just how an attacker can turn a simple string of text into a powerful weapon. First up, we've got a true Hall of Famer. This is the one every developer should know by heart. Using SQL injection to just waltz right past a login screen, no password needed. It's shockingly simple, and against a vulnerable app, it's incredibly effective. So here's how it goes down. The attacker types a weird little string, OR1 equals 1, into a login form. The vulnerable application doesn't check it, it just sticks it onto the end of its database command. The final query ends up looking something like this: find me a user where the password is nothing or 1 equals 1. And since 1 always equals 1, the database says, yep, that's true, and lets the attacker in as the first user in the database. Just like that. Okay, that was bad. But let's take it up a notch. This next attack doesn't even bother with the database. It goes straight for the server's operating system. And the goal here is nothing less than a full system takeover. Okay, picture an app feature where you can type in a file name. The attacker provides what looks like a file name, image.jpg, but then they add a semicolon and another command. See, in a lot of operating systems, that semicolon is a magic character that says, okay, that command is done, now run this next one. The server does its job, and then it executes the attacker's command. Maybe one that dumps a list of all the user accounts on the system. From that point on, it's pretty much game over. So the big question is, if we've known about these attacks for decades, why are they still everywhere in 2025? Why do smart developers keep building applications that are vulnerable to them? Well, the reasons are pretty deeply tied to how we build software today. Really, it comes down to 3 main things. First, developers just implicitly trust the data coming in. They assume input from a form or an API is safe. It never is. Second, bad habits, like building commands by just mashing strings of text together. And third,
Modern applications are just complicated. You have microservices calling other services, APIs all over the place, data comes into the system from dozens of different paths, and it's almost impossible to keep track of it all.
Okay, enough about the problem. Let's talk about the solution. The best part about injection flaws is that they are 100% preventable if you know what to do. So let's lay out a clear 5-rule defense plan to build stronger, more resilient apps.
Rule number 1. This is the big one, the most important one. Always use parameterized queries or prepared statements. This is a way of sending your command to the database first, with placeholders for the data. Then you send the user's input separately. This way, the database knows what's code and what's data, and it never gets them mixed up. This one habit stops most SQL injection dead in its tracks. Rule number 2 is simple. Trust nothing. Every single piece of data that comes into your application has to be validated, always on the server side. The best way to do this is with an allow list. That means you define exactly what good data looks like, say a 5-digit zip code, and you reject absolutely everything else.
Okay, rule number 3 is about what you send back out. Anytime you're displaying data that a user gave you, you have to encode it properly. So if you're putting it in an HTML page, you turn characters like the less than and greater than signs into their safe versions. This is your number 1 defense against cross-site scripting. It ensures the browser always treats the user's input as text, never as code it should run.
Rule number 4 is all about damage control. It's called the principle of least privilege. Basically, your application's account on the database should only have the bare minimum permissions it needs to do its job. If it only reads data, it shouldn't be able to delete tables. This way, even if an attacker finds a flaw, the amount of damage they can do, the blast radius, is way, way smaller.
And finally, rule number 5, you have to automate. You can't catch everything by hand. You need to build security testing right into your development pipeline. That means using tools like SAST, which scans your code for problems, and DAST, which tests your live application from the outside. These tools work tirelessly to find vulnerabilities early, when they're cheapest and easiest to fix.
And let's not forget why all this is so important. When an injection attack succeeds, the impact is devastating. We're talking massive data breaches that make headlines, servers being completely taken over, customer accounts hijacked, and that's before you even get to the huge financial losses, the damage to your company's reputation, and the potential for serious regulatory fines. The stakes are incredibly high. So I want to leave you with this one thought. Think about the application you're working on right now. It probably has hundreds, maybe even thousands of different inputs. URL parameters, API endpoints, form fields, headers. After everything we've just talked about, can you say for certain that every single one of them is secure?